All right, welcome or welcome back for another lecture. Should be lecture number 5. I think we're going to be diving deeper into amino acids and proteins today, but we'll see how far we get. But yeah, don't want to keep, I guess, my student waiting. Hello, hello.
Whoa, hello.
Can you? I can hear you loud and clear.
I
Everything
can
sounds good.
hear you. Yes,
Sorry to keep you
hello. Let me
waiting.
get that off. Get this up.
Yeah. 1 second. I'm gonna start.
Good. There we go. I fixed the thing.
Let me share my screen to start off with. That would be
Nice.
helpful.
Yes. Can let me. Discord. Nice. All right, just bear with us for one moment here, chat, while we get this all set up. It'll only be but a moment. There we go.
All right. Yeah, your camera's coming in. Good.
Yes, I just gotta figure out. Oh, it is a desktop scene. Okay. I'm going to just duplicate this quick. I don't know why it. I don't know why it wasn't there in the first place, but all right.
I like the
I am
classroom
pretty
background.
much ready. Thank you, thank you. Yeah, we're fucking rocking that fucking straight up class vibes. All right, okay. I am ready in 15 seconds. All right. We are here.
All right. 1 moment. I think everything's set up
All
on
right.
my end in record time for me.
Good shit. We did the thing. Okay, I'm gonna unmute the stream. Awesome. Okay. We
All right.
should be good and ready to rock.
Cool. Well, I'm going to unveil the curtain. All right.
Oh, here we go. Woo! Yes.
So
I
we're
love the sounds.
starting off with some questions, just a couple.
Nice. Okay.
Because well, we covered quite a bit of DNA, but we're definitely going to revisit DNA and RNA, not the next chapter. So right now we're on chapter 2, okay, and then chapter 3 is more protein stuff, and then chapter 4, I believe, is we do a super deep dive on DNA, RNA, and all that stuff. But, just to, again, get some of the fundamental concepts of DNA, hopefully, mastered, which I think you pretty much have it there or close to it.
Hopefully.
So, when nucleotides base pair, what type of bonds hold them together? So, are they ionic bonds? Are they pair bonds? Are they hydrogen bonds? Or are they covalent bonds?
Well, I hope that I'm not doing George Bush Jr. wrong when I say fool me once, shame on you. Fool me twice. Fool you can't get fooled again.
Exactly.
And I feel like this is the one I got wrong last time with hydrogen bonds, because I said, how are there hydrogen? I'm going to go with C, and it was explained to me. C, hydrogen bonds.
And let's go with the drum roll.
Oh.
You are correct.
Fool, you can't get fooled again. Let's go.
Exactly. What holds them together? Okay, and well, that leads into my next question. Okay.
Oh, shit.
Which is when adenine and thymine base pair,
I know
how
this
many
one,
hydrogen bonds are formed?
I know this. I know
Is it
this.
0? Is it 1? Is it 2?
Mm.
Or is it 3?
Well, the other time it was C and G, and I said 0. But that wasn't the answer. The answer to that was 3. But the answer to this is 2. And once again, I'm going with C. There are
C?
2 hydrogen pairs, and it is less strongly tied than the other one.
All right. Drum roll. It is, in fact, 2.
Let's fucking go!
So you get confetti.
God damn, we did the thing.
Yeah, so, well, yeah. you know pretty much the ins and outs, okay, of DNA. Like, you definitely know nucleotides, right? You're familiar with that term now. You know the fundamental concept of nucleotide. You definitely know C and G and the 3 hydrogen bonds. And now you know A and T. And that's pretty much like the fundamentals or the foundations of DNA. And so when we're talking about, you know, the sequence of DNA, we're talking about that sequence of A's and T's and C's and G's.
Hell yeah, chat. And if you were here the whole time, chat, you now are fucking masters of that too.
Exactly.
God
right.
Damn.
But we're going to be revisiting this, okay, in way more detail. Well, we're also going to look at RNA because we haven't taken a detailed look at RNA. But if you know DNA, okay, RNA is arguably much simpler. But today, okay, last time we started on amino acids, okay, and building up to proteins, because we're going to be talking a lot about proteins and amino acids pretty much consistently, especially once we start doing a deep dive, you know, on metabolism. There's a lot of protein stuff involved, but the building blocks, okay, of proteins are amino acids, okay, and so we showed this last time, okay. So last time we went sequentially, okay, through the amino acids. There's 20 of them, okay, and here's the table of 20 of them that we classify them by this, you know, popular classification system. And we're going to go in a little bit more detail on some of this classification of, you know, what does it mean when we say acidic? What does it mean when we say basic or positive charge? What does it mean when we say uncharged polar, blah, 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 and then the other half of the table of nonpolar. But basically, these are what we call your 20 canonical amino acids, the building blocks, the Lego blocks of proteins, okay? As in, nucleotides are the building blocks of DNA, okay? So amino acids are the building blocks of proteins that we're going to see. So, diving a little bit deeper into the amino acids, okay, there's the side chains aspect. We covered a little, I think we pretty much mostly, I think, stopped around here last time, but I want to revisit it. Where, yeah, the side chains, okay, of aspartate and glutamate are very similar, okay, both structurally and chemically. They're grouped the same. They're both acidic, okay, and I think today we're going to do a little bit of a deeper dive on acidity and what does it mean to be acidic, and why do we call them amino acids, right? What makes amino acids amino acids? But the important part, at least for now, is that aspartate and glutamate, they have a negative charge at the end of their side chain. What I've circled there in, you know, the purple or magenta, you know, circle. And the only difference between glutamate and aspartate is that that extra CH2 group that I've put there in the red circle, okay? But again, if you're not used to seeing these, you will get used to it because we're going to be seeing these like over and over. It's just a matter of like repetition at this point, getting in the reps. And then, okay, at physiological pH, I'm emphasizing this, but, you know, I'm going to provide more detail of what do I mean when I say physiological pH, but I'm just introducing the term now. But yeah, their arginine, lysine, and histidine have a positive charge, so they're on the opposite end of the glutamate and aspartate. They both have charges, but aspartate and glutamate, they have negative charges, and here these three, they have positive charges, okay? But, as I sort of put there in the notes, they don't always have a positive charge. Rather, under physiological conditions, the conditions of the body, they have a positive charge. And I'm going to provide more detail on that in a little bit. And yeah, just also as a note, the positive charge on histidine there is not shown, but it is supposed to be there. Again, under those physiological conditions that I'll provide more detail about. And then, okay, you have our uncharged polar amino acids. And I think we ended on polarity last time, but we're going to revisit it. And I'm going to try and answer one of the great questions that you asked last time, okay? In terms of, I used the examples of carbon dioxide and water, and you saw that they were different, and you essentially asked, well, why are they different here? I'm going to try and answer that question a little bit better. But yeah, just as a little bit of a review, okay, these groups of amino acids, asparagine, glutamine, serine, threonine, tyrosine, okay, they do not have full charges in their side chains, okay? So they have partial charges, as in they have polarity in their side chain. And I'm going to, again, try to provide more detail on what that means. But yeah, all that to say is, the important part is they have partial charges, not full charges, like we just saw in the past 2 slides of aspartate and glutamate, with the full negative charge, and then the lysine, asparagine, and lysine, arginine, and histidine as the full positive charge. Okay, just those are like the main messages, or the take-home messages that I want to emphasize. And then, lastly, at least when it comes to the groupings on the table, okay, I showed again this last time, we have your non-polar, okay, where basically there's essentially no charge at all, either full charge or partial charge. They're neutral, okay, they're just like chilling. And since, okay, they are non-polar, we also classify them. So technically, okay, non-polar and hydrophobic are like distinct and separate concepts, but very often they are used interchangeably, as in like we use the term non-polar as like a synonym for hydrophobic, but they're technically sort of distinct concepts. But either way, if you're not fully aware of what hydrophobic means, I mean, hopefully it's a little bit intuitive in the term, but we're going to be revisiting this concept consistently throughout, where pretty much everything that I'm laying down here is the fundamentals. Like, there'll be consistent themes throughout, the course or the textbook. And I think I asked you this last time. So what do you think hydrophobic means?
That it repels water or like pushes off water.
Exactly.
Doesn't like water.
And then if you can venture a guess, what do you think the opposite of hydrophobic is? What do you think that term would be?
Hydro loving.
Yeah. So in the English translation, okay, you are right. Okay, but just like phobic is like there's like I think a Greek root for that.
Phobophile.
So something loving.
Hydrophile. Hydrophilic.
Yeah, perfect. Exactly. Hydrophilic.
There we go. Fair.
Where basically the polar amino acids, okay, and the ones with charges, they are hydrophilic, okay. But again, I'll be introducing that concept, but just as a preview now, and also just to get familiar with some of the terminology now, where you pretty much nailed it. Where the opposite of hydrophobic, so afraid of water, the opposite is water loving, and that's hydrophilic.
So kind of like the shit you spray on your shoes to make the water beat up in the rain is hydrophobic, but then like a fucking one of those squeegee rub things are like hydrophilic.
Yeah, so
ShamWow things.
So, and also, try to relate it to everyday life of like, well, do you drink coffee?
Yeah, I love coffee.
Yeah, well, and I know you drink Tim Hortons coffee every once in a while, or
yes,
I've seen you post about it,
and very so much.
And so when you add sugar, okay, to your, assuming you add sugar or something to your coffee,
very little.
Yeah,
it depends, but Tim Hortons, I have to add a bit because it's not great. But yes.
but but even the little bit that you add, like it
Yes.
dissolves, right? Like
Yeah, yeah.
you stir it. Now if you add, let's say, a drop of oil, okay, would you expect that to dissolve in your coffee?
Um, I don't know. Like, I wouldn't expect it to like, yeah, maybe it would like float. Like, yeah, like a drop of oil. Yeah, it'd probably float. Depends on how thick that bad bitch is. But like, yeah, like oil is pretty gloopy. Yeah, that shit fucking. It wouldn't. Yeah,
Yeah,
maybe if you stirred it in, it would probably like get all flinky duke, and then left over time, it might separate. But
yeah. Like unless you're consistently stirring it, okay, and you're like, and even then, you're
Mhm.
not dissolving it. Technically speaking, you're
Yeah,
dispersing
yeah.
it, okay. But
Hmm.
yeah, like you said, but so using the sugar example, like virtually no matter how long that you let it sit, okay, the sugar is not gonna like fall. You're not gonna see it at the bottom of your cup, right? Unless you
Yeah,
like really dump like there's more sugar
yeah,
than coffee in your coffee.
yeah, yeah, yeah.
And so, okay, and I'm introducing these terms now because, well, that relates, okay, that relates to the structure of amino acids, as in
Mhm.
there's a reason why, okay, there's an overlapping reason why, okay, the sugar dissolves in your coffee, okay, and the hydrophilic amino acids, as in the hydrophilic, they're water loving, so they dissolve in water, and then these hydrophobic amino acids, okay, they would
Mm.
not dissolve in water. They would behave like oil in water or oil in your coffee.
What
And
about
Go ahead.
this is a dissolved question. So like when I clean my rigs or like my bongs, I put like salt and isopropyl alcohol. And the isopropyl alcohol does not melt or doesn't dissolve the salt. If I put water in it, it would. But if I put ISO in there, it's good for like scrubbing, you know, like it goes in and like knocks the shit. It's like a scrubbing thing, but it doesn't dissolve the salt.
Yep.
So is that like a hydrophobic, hydrophilic shit, or is that different?
That is a fantastic and pointed question. Okay. So, and that actually overlaps. Let's see if I can bring it up. So, yeah, isopropyl alcohol. Okay, that is technically okay. And now that you asked it, I'll provide more detail on isopropyl alcohol next time
Mm-hmm.
and show.
Cool.
I'll prepare a slide about that.
Oh
But
yeah.
technically speaking, isopropyl alcohol, for it to classify it based off of polarity, okay, it would be polar, but it would not be like strongly polar, where it would sort of resemble, let's say, very loosely speaking. If you can, let's say, see serine here,
Mm.
the first one, okay, might be hard to make out, which I'm sort of maybe covering it up with my little cursor there.
I can see it. That's fine.
But like, yeah, at the end, okay, at the top of serine, there's a little OH group, okay, an oxygen and a hydrogen. So technically speaking, when you're talking about alcohol, that's pretty much the same as alcohol, as in isopropyl alcohol, ethanol, which is drinking alcohol,
Mhm.
methanol. Definitely do not drink ever methanol, unless you want to whatever, end yourself.
Roblox.
Yeah. But
That'd probably
what
be a pretty shitty way to do it. Like that would suck. That doesn't sound like. That sounds like it would
uh
hurt.
yeah, it would not be fun.
Even
But
if you're on a
that's
Roblox, don't do that.
but definitely sort of in an organic chemistry aspect, okay, that OH group, okay, is what sort of,
Mhm.
that's by definition like an alcohol, as in if it has an OH group attached to a carbon, like serine does here, as in at the end there you have OH, and then attached to CH2, that OH is attached to a carbon, okay, that's the exact same phenomenon that you would see in isopropyl alcohol, that you would see in methanol, that you would see in ethanol, okay? And so isopropyl alcohol is polar, okay? But here, the devil's in the details of like, we're going to see that there's like a spectrum there. Like something can be like strongly polar, and something can be, medium. And I sort of actually hinted it
So,
there with my note of like cysteine is missing from the table because it is considered like mildly polar.
and does it have to be OH group? Like, what about tysosine? Is that an alcohol or like hose or no?
So
Only
tech,
O's, no
uh,
hose.
good, yeah, very also pointed question. So yeah, technically speaking, also okay. It would have so that OH, it has an alcohol group, but it also has like other things as well. Okay, but you're absolutely right. The tyrosine, that OH, okay, it's pretty much the roughly similar to the serine, as in like in an organic chemistry aspect, that OH would give it alcohol property, so we can put it under the category of like alcohol. You're going to see when I prepare the slide for isopropyl alcohol for next time, you're going to see that there's going to be an OH there attached to a carbon, just like you're seeing here with serine, just like you're seeing here with tyrosine. Okay, and that's what gives it the polarity, because oxygen is electronegative, but we're going to see that in a future slide. But yeah, pretty much there's a huge overlap of what you observe with isopropyl alcohol, and let's say what's going on with serine and what's going on with tyrosine.
And is there a reason why tyrosine has HO and serine has OH? Like, is there like a structural difference on which one comes first?
That's just yeah,
That's just difference. This is like how it's written.
Yeah, exactly. Just that's just they have happened to write them differently. But at the end of the day, that hydrogen, that H is attached, is covalently bound. Now that you're familiar with the term covalent bond, the hydrogen is covalently bound to that oxygen. Absolutely. Good question. Awesome. I'm glad that you noticed that, because that is that's a small detail that can be overlooked. So I'm glad that you're asking that. So and going back to like your cleaning things, like there's a reason why. Okay, let's say, do you have let's say a Sharpie? Have you ever used a Sharpie?
Yeah, I got one. Okay. Should I grab it?
If you want to.
Sure, it's right here. Here's a Sharpie. Here's a couple of pink and a red Sharpie fucking marker.
And have you ever, let's say, written on, I don't know, plastic or glass with them? Okay. And then, do they come off with water?
Not well. But they can if you scrub hard enough. But like they're pretty.
You pretty much have to scrape it off. Like the water is almost like inconsequential.
Yeah. The water doesn't help much. No. Like if anything, it helps it like just like sound less harsh when you do it.
Exactly. But have you ever tried with the isopropyl alcohol?
No, I haven't.
You should run that experiment before next week and report back to me. Or you can do it now if you want. I don't know if you have isopropyl alcohol with you or not.
Yeah. Well, I do. I always stay strapped to that ISO. Hell yeah. Fuck yeah, I'm a stoner, baby. Of course I got that ISO on me. 1 second. All right. And all right.
So
I also have a piece of glass here.
Yeah, if you want to just, right.
And I got a little bit of water. We can
just scribble. Although those are like Sharpie brand Sharpies.
Yes. I will do it on the bottom. I will. So here's my rig. I'm going to put if all else fails, I have a little fucking pentagram on the bottom of my rig, and that is totally okay. But let's see. Can you see that? Yeah, you should be able to see that in the camera.
I can see that. Yeah, absolutely.
All right. And because of isopropyl is how I keep my rig somewhat clean, but fucking it gets kind of dirty. But all right, so there's the star. We'll get a little bit of toilet paper. We'll get a little bit of water on it. I'll try to scrub. All right. It is coming off a bit, but
with this is with the water, right?
Yeah, this is with the water. It's coming off a bit, but a lot of that is elbow grease. But there is still a visible. I don't know if you can really see it
I can make it
on the light, but Yeah, and I will try the ISO. You can get a little fucking toilet paper. Give it the good old fucking. Put that
Although,
paper on the
you know,
top and give
Sharpie
her a
might have
shake.
like changed
Their formula.
their formula. Yeah, exactly.
No,
So
but it
there's
doesn't come up really well with the water. But we got that there. Oh God, I could have just like touched it.
yeah, yeah, you could exactly. They're just super easy.
It's yeah. And it's great for removing like laws, and you can see like my thing is just like
Yeah,
red now.
there you go.
Um,
That's what I would
whereas
expect.
the paper before is just a little bit, and I scrubbed this. I like touched it, and it's like all there. This thing is clean as a fucking whistle, my dude.
And
Look at
and and,
that.
and so based off of now of what you know of the terms of hydrophobic and hydrophilic, okay, with the Sharpie, okay, how would
Mm,
you describe it?
I would say that it is hydrophobic. It doesn't like the water. Push that shit off. It doesn't even give a fuck about that shit. But it gives a
Exactly.
fuck about the ISO.
Exactly. And the ISO, okay, even so, uh, here's where it's the nitty gritty details, okay, where pretty much as you said and as you experienced, like even with just like the gentle wipe with the isopropyl alcohol, it just like melts right off, pretty much.
Hmm. But
Uh,
also, fucking, I have a little thing of water here that I use for my humidifier. And this, I leave this out for days and not really worry about it evaporating. But if I don't put the top on this for like 30
yeah,
seconds, it's
yeah,
gone.
exactly.
Yeah.
And so here is where the difference is. Okay, so technically speaking, water is a polar molecule. Isopropyl alcohol is also a polar molecule, but it's much less. Okay, we're going. I'm going to prepare the slide for next week because like this is really good. Well, yeah, really good way for the real world experience, and you know how your knowledge can translate to real life. Where since the isopropyl alcohol is slightly more hydrophobic, okay, not slightly, well, moderately more hydrophobic in comparison to actual water, okay. We're going to see this actually in a few slides. There's this aspect in chemistry and biochemistry of like dissolves like, okay, where polar molecules will dissolve other polar molecules, okay, and non-polar molecules will dissolve non-polar molecules, or hydrophobic molecules will dissolve hydrophobic molecules. As in the Sharpie, as you literally just experienced, it is hydrophobic, or like you really got to like the water. I mean, pretty much probably even with a dry paper towel, if you just like prepare enough force,
Yeah,
the water
right.
doesn't really
Yeah.
get you there. But with just a little bit of the isopropyl alcohol, just like a gentle, one pass, and it's like all gone or just like melts off. And that's because, okay, the Sharpie, because I know since I use them in the lab and there's a reason why Sharpies are designed to pretty much resist being wiped away from water, because they're very often used in the lab when we work with a lot of water. We don't want just when we're labeling our things, just like a splash of water gets rid of all our labeling, okay?
Yeah.
And so, since the ink in a Sharpie is organic and non-polar, okay, and I'll try to show you like the structure of the ink in a Sharpie, and you'll see that it'll overlap more with the isopropyl alcohol, okay, as in like will dissolve like, as opposed to water, H2O, where basically the ink in the Sharpie is like hydrophobic. And since isopropyl alcohol is also moderately hydrophobic, okay, it will dissolve it pretty easily, as you just saw. And so that's the relevance.
Yo, so if I said to my fucking homie that was trying to clean their fucking rig with just like shaking it in water, that they were being silly because the dab is too hydrophobic and they need to get something more polar to clean it, would that be a correct statement?
You need something more non-polar. Well, it depends.
Less
Like,
polar.
yeah, exactly,
Less polar.
exactly
It's too
right.
polar.
Yeah, exactly. Where since I don't really know exactly what the residue in your bong is, I'm more familiar with Sharpie ink than bong residue. But like basically, if the bong residue is like less water-like, okay, then you would need something that it's less water-like to dissolve it.
It's
Basically.
goopy.
Yeah, Exactly.
Ah,
And this is, chemistry, biochemistry in our everyday lives.
look at that.
And well, this segues or transitions nicely into polarity. Okay, where what does it mean to be polar? Okay, and well, my standard example of a water molecule. Okay, and I showed this last time. Okay, and now I'm going to also again try to answer the question that you brought up great last time in terms of why does water look like this bent or like angular formation. But what does polar or non-polar mean? So yeah, water molecule, since the water molecule has a partial positive and negative charges, it is a polar molecule, okay? You have partial negative charge on the oxygen. Since the oxygen is more electronegative, okay, even though between the oxygen and each hydrogen, it's a covalent bond. They're sharing electrons. The sharing is not equal. Oxygen is greedy, okay, or it's stronger when it comes to trying to grab electrons towards it or pull them towards it. You get this partial negative charge on the oxygen, and that creates a dipole, okay, across each bond, and that makes the overall water molecule polar, okay? And then to contrast that with non-polar, okay, and well, yeah, also the 3D shape of a molecule also matters. I'm also going to try to answer that question again of why does it matter. But despite having partial positive and negative charges, carbon dioxide is non-polar. Okay, so you still have a dipole. Okay, you have a partial positive charge on the carbon in the middle. You have partial negative charges on each oxygen on the ends, but since, okay, they're on opposite ends, they're sort of like canceling each other out, which I'm going to show on my next slide. Where, yeah, it's a tug of war for electrons, where since oxygen is more electronegative than hydrogen, oxygen wins the tug of war. In carbon dioxide, since there is an oxygen on each end, okay, on opposite ends, I like to think of it as an actual tug of war of like oxygen is pulling from the carbon, okay, on the left-hand side, and oxygen is pulling from the carbon on the right-hand side. But ultimately, okay, nobody wins. You can think of it as like forces moving in equal and opposite directions. As opposed to in water, okay, they're not equal and opposite directions. And so there is no net dipole on the carbon dioxide. Okay, that's the ultimate critical difference. Where in the water molecule, okay, you have a dipole across each bond, as in this bond here, okay, between oxygen and hydrogen, this bond here, basically both purple dashed lines. But since they're not equal and opposite, okay, there is a net dipole, okay, as opposed to in carbon dioxide, you both have dipoles, but they're in opposite directions that I'm going to show on the next slide. Okay, so that's ultimately what's happening here, where you have, just like in a magnet, you have a north pole and a south pole. That's pretty much where we get the term polarity from, so to speak. But to be a polar molecule, you need partial positive and negative charges, which both water molecules and carbon dioxide has. But the difference is you also need a net dipole moment. So there is a net dipole moment on water, but there is no net dipole moment on carbon dioxide. Okay, that's the key fundamental difference of what makes water the polar molecule and the carbon dioxide not a polar molecule. Okay, because the arrows in the water molecule are going in the same direction. They're both going towards the oxygen, okay? As opposed to in the carbon dioxide molecule, one's going towards one oxygen and one's going towards the other oxygen.
And it's because the negative sucks the shit towards it, essentially.
Yeah.
To like visualize it. It's the negative fucking that's just like shoo.
Yeah, exactly. As in since oxygen, let's say number one, whichever one you want to put, let's start with the left-hand side, it's like whatever, it's trying to suck electrons towards it, okay? Specifically, it's trying to suck electrons towards it from the carbon, as in carbon stuck in the middle, okay?
Yeah.
And so, like, it's almost like, think of it in terms of, like, if you're a person, if you're the carbon dioxide, and
you're getting double teamed.
Yeah. And if you have, like, two people, okay, holding your arms, or pulling on both your arms, like, and they're both of equal strength, and they're pulling in equal and opposite directions, you don't end up moving, okay? That's ultimately what's happening of, like, carbon stuck in the middle. Like, carbon, basically, carbon is, having its electrons, sucked away from one oxygen on the left, okay? But at the same time, simultaneously, the oxygen on the other end is also trying to suck electrons from carbon on the other end, and so there's no net movement. Since they're both equal and opposite, they just cancel each other out. That's effectively what happens. But in the water molecule, since the oxygen is in the middle now, okay, and the oxygen is much stronger than both hydrogens, okay, then it just wins the tug of war of, like, yeah, well, I can suck away from both hydrogens, no problem. And that's why you have a net dipole on the water molecule and no net dipole on the carbon dioxide molecule, okay? And so, does that clarify it a little bit more?
Yeah. The understanding that the shit goes towards, like, the negatives, I think, helped a lot, because I was pretty much about, like, why are they moving that way? Like, how do we know that? Like, why? Like, I only know that because you're telling me that. But then it made sense after that.
You're absolutely right. And well, now that you brought that up, I'm gonna prepare another slide on, because I introduced the concept of electronegativity. And it's like, yeah, I just, like, threw it out there in terms of electronegativity means, like, you're strong in your ability to pull electrons towards you, but I didn't provide a little bit more detail. But I'll prepare a slide next time to provide more detail on, like, on electronegativity and what that means, in more detail. Because it's a really good question, and I just kind of, like, threw it in your face. And I don't want you to take it on faith, okay?
No, I appreciate it. Yeah, no, okay, that makes more sense.
So, and you going back, so we stopped here last time, okay? And last time, you asked the great question of, like, well, why is it that water is shaped like this and carbon dioxide is shaped like this? So, like, yeah, it's that straight line, and that three-dimensional shape that's consequential, as in, if carbon dioxide wasn't linear, okay, that's what makes it equal and opposite. Of, like, if it wasn't a straight line, well, then the arrows that I pointed, they would not be going in opposite directions, okay? And then you would potentially have a net dipole, okay? So the structure is a factor when it comes to polarity. And you asked the great question of, why is water like that, in sort of like an upside down V, or what's upside down when you're a molecule. But either way,
an Illuminati triangle.
Yeah, maybe. And then why is carbon dioxide linear? Okay, and so that's what I'm going to attempt to answer now, but right before that, okay, just to, I guess, give you, your textbook definition of, like, polarity, where coincidentally, okay, they use the same example that I do, or maybe since I've read this so much, their example just, like, seeped into my brain, and I just subconsciously prepared the same slide. Who knows who is plagiarizing who? I don't know. But yeah,
they're plagiarizing you. I know it.
But that's essentially what they say, the same thing. I'm just putting it, just for informational purposes. If you want what the textbook says, this is what it says. So, like, yeah, there's no net dipole moment because you have these arrows here going in equal and opposite directions, as opposed to in the water molecule with that bent shape, okay, as well. That matters, where the arrows are going, and also, well, the key difference here is oxygen is in the middle, okay, and it can just overpower the hydrogen atoms very easily. Okay.
And is the vertical line on the arrow, like, depending on how big the D is?
You're technically, yeah, as in, so the D, like
1.85 D, is that why it's only there? Because that's 1.85 D, but, like, let's say it was like 3.85 D, would it be farther up?
Yeah, it would be bigger, like, as in, like, we can calculate the net dipole if we want to. Although for
So
us
the
as biochemists, we don't really. But they're pretty much like saying with that arrow there in this figure here, they're saying like this is if you sum the two arrows on the water molecule, here's like your giant arrow in the middle.
So the you see, oh, okay. So like that, what I'm talking about is, I thought that was showing, explaining that. So like, you know how the arrows are there, and then they have that line that goes through them towards like the bottom, like
Oh yeah,
eight.
yeah, that little
Does
cross like
that,
thing.
yeah, does that matter, and does that move like
Uh
depending on something, or is that
oh
just like to
no
make it
no.
look
So
cool?
that's that's our fancy way. Okay, so I going back to my slide here. So I've put in the partial charges there, as in yellow and red, the red symbols, partial negative in yellow, partial
Mm,
positive in red. Okay, to make it, since you're not familiar with the symbols and terminology we use.
mm-hmm.
So pay attention to where the positive charges, on the water molecule are, and
Yeah.
on the carbon. Where on the water molecule, the positive charge, is on the partial positive. Sorry, partial is on the hydrogens, and the
Mm-hmm.
partial positive is on the carbon in the middle.
Uh-huh.
Okay, and positive, we symbolize that with a cross, right, or a plus sign. Uh,
Mm-hmm.
and so with that arrow, that cross there is basically
To show the positive.
exactly right.
That makes sense.
Where in the carbon dioxide, the cross is pointed towards the middle, the carbon in the middle, as opposed to in the water molecule, the cross is oriented, towards the hydrogen atoms. And then basically the arrowhead, the pointed arrowhead, is all supposed to be pointing towards the partial negative end. Okay. And that's sort of our shorthand, or if we don't want to start drawing in partial signs, we just draw in that arrow because we're lazy. Like that's also a consistent theme of scientists are also lazy. So yeah, that's your textbook definition, and then to hopefully provide more detail and an answer as to
Oh, cool. I like the
why.
dots. Those are fun. I like that. They look
Yes.
like they're having so much fun. Oh my God.
So
Carbon dioxide is like so cool, dude. It's just having so much fun. Yo, look at that shit. Oh my
yes.
God. Everyone's having a good time.
So why does carbon dioxide have a linear structure and water molecule does not? Okay, and it has to do with basically electrons. Okay, where in the water molecule, so the bottom, we call those Lewis structures. Another way of depicting, there's multiple ways of depicting molecules and compounds, etc. But at the bottom, this is one version that we call Lewis structures, where there's this set of electrons, that pretty much push the hydrogen atoms down, because electrons, they are negatively charged, and they occupy space, and so they don't want to crowd around them. Let's put it that way. And so when they kind of want to, they pair up, as in each dot represents one electron, and you see that they sort of like they come in twos or pairs. Technically call them lone pairs of electrons. But basically, you have one pair of electrons, sort of on the left there, and then one set of electrons on the right, one pair of electrons on the right. And yeah, since they're negatively charged, and since they don't want too much of a crowd around them, they're propped up there like in space. That's where the empty space is. There's no hydrogen atoms around, or rather, they're like forcing the hydrogen atoms down. They're saying like, hey, get out of my way. I need some empty space around me. And that's why you have this bent shape in the water molecule, as opposed to in carbon dioxide. Since carbon is in the middle, carbon does not have any in this depiction here. Well, in carbon dioxide, there's no extra lone pairs of electrons, as in all the electrons are occupied, basically. There's no free floating, so to speak, electrons. And so you have just the double bonds, and so there's nothing to like push those around, and so and since we want to, when we want to maximize space, we don't want too much crowding, basically.
Yeah,
And atoms.
that's. Oh, sorry.
No, that's okay. If you had a question, go for it.
Oh, no, no. Continue.
where basically, atoms and electrons, they don't want too much crowding. And if it's, let's say, if it's a tug of war between, empty space between an atom and a pair of electrons, generally speaking, the pair of electrons like wins. It says like, get out of my way, and that's what's happening. Of like those on the water molecule, those 4 electrons or those 2 pairs of electrons are pretty much saying to the hydrogen atoms like, get out of my way, you got to go down. And that's why there's that bend shape. And so you don't have that occurring in the carbon dioxide, or you don't have that occurring in the carbon in the middle. Doesn't need to push anything around. And the oxygen atoms, okay, there's a reason why they're linear, because oxygen on the right hand side, it has a bunch of empty space there, and then the other oxygen, it's just going to sort of like naturally spread out to the other ends, like when they want to maximize space. There's a reason why like the oxygens are not like right next to each other, because they just want to like maximize space.
Yeah.
So that's why you have this particular structure in the water molecule and the carbon dioxide.
That makes sense.
That was a really good question. I'm glad you brought it up. Does that clarify it a little bit?
Yeah, no, a lot. It makes me want to play Mario Sunshine. I didn't even like that game. I don't know why. It's like the pictures are so fun, and they look like the flowers from that. And there's
well, if you like cool. These,
I like these. These are cool.
Because like this is in generally speaking, in first year university chemistry, like you have to draw these structures like over and over. You have to sort of like master these structures. Well, maybe I'll start incorporating, because there's totally questions I can ask about Lewis structures. But maybe I'll come up or start incorporating some questions if you like these structures.
They're cool. They're fun.
And there's totally ways. There's totally drawing these structures is a skill. That if you like them, I have no doubt that you can master that skill.
Hell yeah, let's go.
So, a little bit more on polarity. So yeah, and this is where I said that like dissolves like, and that's where we're revisiting where polarity is important to understand the chemical properties of the amino acids, but also how they behave, dissolve in water. Same thing with, again, the Sharpie, and pretty much this is the phenomenon, or like largely the phenomenon as to why the Sharpie, when you use water, doesn't get rid of it. Well, when you use isopropyl alcohol, and you could even, I don't know if you have, let's say, drinking alcohol around, you could even try it with that, and you should get the exact same result with the isopropyl alcohol. Because there's this aspect of like dissolves like, where water is a polar molecule, okay? So if you're another polar molecule, okay, then water should dissolve you pretty nicely. As in the sugar, let's say if I asked you based off of this to classify the sugar that you add in your coffee, do you think that is polar or non-polar, given the fact, I should add this, of you can consider your coffee basically a water solution?
Polar.
Yes.
Well, yeah,
you're exactly right. Where sugar, as we will see,
it likes water and it dissolves.
Exactly. Where, I don't know if you happen to, I don't expect you to know, but let's say sugar. Do you know potentially a fancy word for sugar?
Fancy word? Like glycol? No, not glycol. Fucking.
You're close, but like let's say if we're talking about, let's say, fats, proteins, and something else.
Sucrose, glucose.
Fructose, yeah.
Sucrose.
Yeah.
Move close.
Yeah, like perfect in terms of like you are naming sugars, but these fall under like a category. I know that you know it for sure. It's just like it's not necessarily intuitive per se. Where if you look at a nutrition label, okay, you have your calories, you have your fats, lipids, you have your protein, and there should be another
sugars.
Yeah, but that's usually under a sub.
Fructose. I don't know.
Starts with the letter C. Yeah, I know. Carbohydrates.
Calories? Oh, carbs. Oh, carbohydrates and sugars.
Yeah, So, and there's a reason why. There's a reason why we call them carbohydrates, okay? Where
Mm.
the sugar that you add in your coffee, that is sucrose, okay? And that falls under the category of carbohydrates, okay? And we call
Mm.
them carbohydrates because, well, based off of that, can you maybe guess like at least one type of atom that you'd find in a carb?
Carbon.
Yes, exactly. And we call them carbohydrates because, as we're going to see, we're going to do a deep dive on carbohydrates, of each carbon in a carbohydrate is hydrated, as it has technically a water molecule attached to it, okay? So your sucrose that you add to your coffee, it's a carbohydrate. It's polar, and no surprise, it dissolves in your basically your water-based coffee. Coffee is mostly water. Pretty much just about everything you drink is mostly water. And it's pretty much this concept of like dissolves like. Polar molecules dissolve in other polar molecules. Non-polar molecules dissolve in other non-polar molecules. Or another way of saying it is hydrophobic molecules dissolve, so to speak, in other hydrophobic molecules. But pretty much, not super complicated or fancy. Of just like dissolves like. If you're polar, you're going, like your sucrose is polar, it's going to dissolve nicely in your water, and water is a polar molecule. And well, that's pretty much the ultimate reason as to why just about anything dissolves in anything, generally speaking, at least in most everyday life. Of like going back to cleaning the residue from your bong, okay? If water is not doing the job, you have a strong indication that whatever you're trying to clean off, it's not a polar molecule, and you likely need something less polar or non-polar to clean it.
Yep, absolutely.
So that's chemistry in your everyday life. So, getting back to the amino acids, okay, there's a reason why I brought up polarity, okay, because it relates to amino acids. So I've only added this extra note. Of like, we're zooming in on serine here. Serine is in this uncharged polar, so there's no charge, it's a partial charge, but it is a polar amino acid, okay? It's polar because you have that oxygen there, because of the oxygen in serine's side chain, okay? And it is surrounded by carbon and hydrogen, okay? The side chain of serine is polar, where that oxygen atom, okay, since it's electronegative, it can pretty much, pull electrons towards it from the surrounding carbon and hydrogen. So it wins the tug of war for electrons, and so there will be that partial negative charge, okay, on that oxygen atom that I'm pointing to in the arrow. And it's basically a similar theme for the other amino acids in the table. Of like, we're going to get used to seeing these. But like, if you look at the side chain of asparagine, glutamine, you're going to see either, an oxygen, you're going to be seeing like a nitrogen or some sort of, electronegative atom that's, surrounded by non-electronegative atoms, typically carbon or hydrogen, that it pretty much wins the tug of war. And that's why we classify them like this. Just as, I don't know if you recall, you mentioned tyrosine, okay, and you saw that tyrosine has that OH, okay?
Yeah.
It's because of that OH that we put it in this table here. It's uncharged polar. It's the same phenomenon. Since you have that oxygen that wins the tug of war in tyrosine, we put it as uncharged polar. That's how we're classifying them. And then, okay, alanine. So here's the non-polar ones. These are neutral or, hydrophobic, okay? Because the side chain of alanine is just carbon and hydrogen, okay, these are essentially not electronegative atoms, okay? They pretty much have virtually, or we generally consider it like no ability to, pull electrons towards them. And so since there's no tug of war for electrons going on, then no one's winning the tug of war, and so they're like non-polar, okay? And that's pretty much, we're going to see these in more detail consistently. But like, glycine, valine, leucine, you're going to see that pretty much when you look at their side chains, okay, they're largely just composed of carbon and hydrogen. Pretty much, you're actually, just double checking, you're pretty much not going to see any oxygen or like nitrogen in pretty much just most of these side chains. The vast majority of them is all just carbon and hydrogen. Similar to alanine, just maybe a little bit more fancier, just more carbon and more hydrogen. So that's why we put them as non-polar. But, okay, why do we call them amino acids? Okay. Well, the ultimate answer is because of organic chemistry. Okay. Which is not super critical, to know, but still for informational purposes, and, I want to be thorough. There's a reason why we call them amino acids, okay? And there's a reason why, well, it's also important in terms of, like, they're amino acids, they're acidic. Acidity is important. But, so this is what I'm showing here on the left is, like, straight pulled from an organic chemistry textbook, okay? Where, when we're looking, okay, at molecules, we're trying to, just as we classify the amino acids, and I went through the classifications, okay, we also try to, like, classify themes when it comes to molecules. So, like, when we see this motif or, like, this pattern of atoms, okay, well, that's a carboxylic acid. As in, when you have this oxygen, okay, double bonded to a carbon, well, pretty much, when you see what's highlighted in red there in a molecule, we call that, it has a carboxylic acid group, okay? And then when you see a nitrogen, okay, that's surrounded by just about anything, that R stands for pretty much like whatever. Pick your atom, so to speak. And so we call it an amine, as in that molecule has an amine group, okay? And so if you look at the amino acids, okay, here's your general structure of an amino acid, okay? It has an amino group. You have a nitrogen, and it has 3 hydrogens bound to it, as in it fits the criteria of you have your nitrogen there, okay, and the R's in this case are replaced by 3 hydrogens, okay. And then your carboxyl group, okay, it's COO, as in pretty much it's the exact, well, it's 99% the same as what's shown there on the left in red, the carboxylic acid group, but the hydrogen is missing, as in the hydrogen has been given away. And I'll be trying to answer the question why that hydrogen is being given away. But that's why we call them amino acids, as in this carboxyl group is acidic, okay, as in it pretty much fits this criteria here of oxygen double bound to a carbon, and then it has another oxygen there. And then under some conditions, the hydrogen will be there. And then the amino group, okay, you just have nitrogen that's bound to 3 hydrogens, and that fits the amine, classification there, the amine group, and that's why we call them amino acids. On one end, we have an amino group. On the other end, we have a carboxyl group, which is acidic, okay, as in it has given away one of its hydrogen atoms, and therefore we call them amino acids, okay? So now that we've done a little bit of a deep dive, okay, on amino acids and polarity as well, and we're going to be, like I said, we're going to be seeing these like over and over. And I want you, well, not that I want you, it's going to happen eventually, as in you're going to get used to like seeing amino acids and like, oh, I know what this is. But just to maybe get in the habit of, start practicing of visualizing amino acids, flipping them around, because they're not always laid out nicely in like a straight line, so to speak. So that's why I have some questions, a couple of questions lined up of like, can you identify this amino acid? Okay, as in what amino acid is this? And I'm going to give you a little bit of help, like giving you the structure. So here's where, got to get in the habit of like rotating things and getting used to how we depict, molecules and all that stuff. But I'm going to provide more detail on what's happening here. Is it, arginine? Is it lysine? Or is it leucine? Okay, so what you need to know here for this one, so I've mostly focused in on the side chain, okay? And in green here, okay, is, let's say, violating our typical law of, generally speaking, we show carbon as like gray or like black. In green here, green is carbon, Okay.
Mhm.
The rest is the same. Blue is nitrogen. And the hydrogens, okay, the hydrogens are not shown here, okay? So pretty much all you're seeing here is
Um,
carbon and the nitrogens.
I'm pretty sure it's A because I think the reds are oxygens, are they not?
They
Or
are,
no?
yeah, you're right. So that is typically the color theme, okay? Uh,
And it's the only one that has two oxygens that isn't just the amino.
uh, Fair enough. But what I focused in on is because uh, totally,
Mm.
there's a reason why I put glutamate there.
Mm.
Where I focused in on the side chain specifically, as in, I can actually uh, pretty much, you could ignore the oxygen,
I can
where
ignore that. Okay.
yeah, you can pretty much ignore like the top part, basically,
Okay.
and mostly focus on like the tail portion. We're,
Um.
we're based off of that alone.
Okay. Well, then it's probably D because it's just like a long tail with some like night. You said blue is nitrogen,
Yeah, blue exactly is
so
nitrogen.
then D. But D and B both have like not much going on, but there's only one and not two. So yeah, D. Final answer.
All right, and let's see if we can do a drum roll.
Let's
You are
go.
correct.
Woo.
Exactly, it is
Let's
lysine.
go.
That
Big
deserves
dubs.
some confetti.
Let's go.
So,
Bang it.
yeah, the hydrogens are not shown, and so understandably, okay. Again, there's a reason why I put glutamate there as like the first one. Where so in red there, okay, uh, and understandably, it's not super clear unless you're used to seeing these. Uh,
Hmm.
but even though you're seeing like two like red dots or like two red things, uh, that just means a double bond there, not two oxygens, but rather one oxygen that's double bonded to a carbon in this case. Okay, where as we'll see, okay, the top part here, that pretty much corresponds to like the bottom part of just about everything that you see for all of them, as in pretty much what's at the bottom, the N, the C, and the COO minus. Although technically speaking, one of the oxygens is missing here, but that's an aside. Pretty much focus on the side chain. You nail the side chain. That's exactly how you analyze it. It's just a string of carbons, okay, and that one blue at the end, that represents one nitrogen, and
Hmm.
only lysine has pretty much a string of carbons, as in you can,
Hmm.
if you count it, this is
One,
carbon number
two,
one,
four.
two, three, four, and then nitrogen. You can see lysine,
Hmm.
CH2, that's one carbon, CH2, carbon, so four carbons, and then nitrogen at the end there. Okay, so yeah,
Hmm.
nailed it, got it right. Uh,
Woohoo!
and yeah, this is definitely it definitely takes a lot of time in getting used to, in getting the habit. But with that in mind, okay, still pretty much the same thing of like, can you identify what amino acid this is? Is it
Okay.
A, histidine, B, tyrosine, uh, C, phenylalanine, or D, tryptophan?
Okay. Well, it's so I'm ignoring the bottom part and I'm going one, two. There's like two carbons, it seems like, right? But then where's it? Oh, hydrogens aren't shown.
Yeah, exactly right. Exactly. Hydrogens are not shown because we don't, not that we don't care. They're there, okay. But for our purposes, as let's say chemists or biochemists, like we sort of like, we don't really need to know. We just assume that they're there. They're not like critical pieces of information, so to speak.
Um, and then they go off to hydrogen, nitrogen, and then where are these motherfuckers with the goddamn nitrogen? None of these fuckers have. Okay, okay. I didn't see A. And then it goes to CH, and then yeah, it's A. I think it's histidine. Final answer without
Lock it in.
fucking. hurting my brain too much. Yes.
No, like that's why it's like, you know, take some time, because you got to like there's a reason why I could have there's a reason why I depicted it, because it takes some rotation and, you know, getting the habit of like mentally rotating things. So
hey, let's go, baby.
you got it right.
Yeah,
It is
let's
in fact
go.
A. So
Hell
perfect.
yeah.
Getting
Good
in the
shit.
habit.
Let's go.
So I think we covered. I think this is a good place to stop. You don't want to overwhelm you. Maybe as just as a preview for next time.
Let's
Okay,
go.
we're going to be covering, okay, just a brief primer on acids and bases. Okay, why do we call them amino acids? Well, what does it mean to be an acid? Okay, and what does it mean to be a base? Okay, and we're going to go through some. So technically there are 3 definitions of acids and bases. This is one of them. Okay. But as a preview for next time, okay, we don't care about this definition. Okay, we're gonna see what definition we care about. But there are 3 definitions of acids and bases. This is one of them. We're going to discard this one for the time being, or actually pretty much for the entirety of whatever the course of the textbook. There's only one definition of acids and bases that we care about, and this is not one of them. Okay. But yeah, I think you're getting in the habit of like amino acids. That you have DNA down, like mastered the fundamentals for sure, and hydrogen bonding, and you pretty much all on your own got these amino acid questions right. So you're getting the habit of like seeing them, rotating them. So like yeah, like this is going like fantastically, at least in my mind.
Good shit. Hell yeah, no, I think it's going great. I'm learning lots.
And hopefully, okay, now that you have some, I think you have a solid foundation now of polarity, okay, and well, polar, non-polar, and hydrophobic. And hopefully you can maybe now translate that into your everyday life of like, well, what, you know, if I ask you the question of, you know, why do you think, you know, oil, let's say olive oil, you know, if you put it in water, why does your oil and vinegar not mix? Oh, what would be your best?
The polarity fucking is off, dog. They're just fucking, they're not like, dog. They gotta be more like. There's too different. They separate.
Yeah, and if you can maybe venture a guess in terms of like, let's say, for example, okay, so you have, I got this slide here, non-polar, okay, and the non-polar, very often synonymous with hydrophobic, okay, and based off of this, of what I'm outlining here, okay, now, if we start talking about, let's say, you know, your olive oil, I don't know, pick your whatever cooking oil, based off of this, okay, what type of atoms do you think you would find in, you know, your olive oil and all that stuff?
You would definitely be finding them non-polar friends.
Yeah.
Are you asking me which of these amino acids are in the oil?
No. Which atoms? As in, like, if you could venture a guess of,
like.
Oh,
I would say that you're gonna see carbon and hydrogen in those bad boys.
You absolutely will. 1,000%. And if that's pretty much like, as we'll see, and we're gonna do a deep dive on, you know, fatty acids, oils, and hydrophobic molecules. Okay, where pretty much like 99% of, you know, oils and fatty acids, they are just carbon and hydrogen, just like strung together. And that's what makes them hydrophobic, and that's what makes them not dissolve in water.
So none of those friends you showed me earlier were non-polar. They were all polar because they had nitrogens in them bad boys.
Yes, so that good eye, very good eye, where this lysine here, okay. Since you have that nitrogen there at the end, okay, it has some polarity to it, and that, as shown here, you do not see lysine in the table here, okay, and the other answer was histidine, and you do not see histidine in this table.
I don't see it anywhere there, fuck.
So yeah.
The anti-water game.
Nailed it. It's coming together super nicely. I think you should be proud.
Absolutely, hell yeah. Well, I have a great teacher. Thank you very much. It's been great so far. I'm very much loving it and learning lots every day. Well, every week.
And well, I mean, we're still sort of like laying the foundation. You know, this is absolutely biochemistry. But like, you know, we're building up in complexity of like well, I mean, it's all relative, but like amino acids are complex, but we have yet to start assembling. Okay, we're focusing on amino acids like one by one, but next time, okay, when we get to proteins, we're gonna start putting the amino acids together. Like, what happens when you connect 5 of them together? What happens when you connect?
Oh shit!
What happens when you connect 20 of them together? What happens when you connect 5,000 of them together? Which you can that is absolutely, you can connect thousands of amino acids together, and that's what builds up proteins. And we're gonna build up complexity towards that, almost certainly starting next time. But yeah,
can we make our own and shit?
Our own proteins?
Yeah, can we just do like human concoctions?
Yeah. So yeah,
be in the lab cooking up some fucking amino acids and shit.
That's a fantastic question. So these days, okay, protein engineering is a thing, okay, and almost certainly, I think there's a chapter devoted to like protein engineering of like, yeah, we know we have, let's say, a good idea of the proteins in nature. Well, maybe we as humans, we can like make some things better, or we can take some proteins. Well, we do this all the time. I'll bring in some research of like, yeah, this protein, we've taken this protein from nature, we've modified it for our own purposes. Like, this happens pretty regularly these days, through pretty much manipulating the amino acids of like, oh, in nature it has this combination of amino acids. Well, what if we change it where it's a slightly different combination and now it's better, or now it can do something that we want to do that it didn't do before. This is all part of the toolbox of biochemistry, and that you will start understanding these things well, once the knowledge is there, and it's totally starting to get there. So yeah, this has been great.
Hell yeah.
You got questions, concerns, comments, criticisms?
Fucking my concerns are for fucking all the people in the scientific community, because we're about to fucking end it all. We're about to just solve science, dog. Fucking, hey yo, move over, Bill Nye, the whack guy. That's what I'm concerned for. God damn, science is about to be solved week by week.
Yeah,
amazing.
And next, so I'm going to incorporate, I'm going to prepare some of those slides based off of what you mentioned in terms of, yeah, isopropyl alcohol, okay, electronegativity. Yeah, these are all great things to cover. And you, yeah, as usual, you always ask fantastic questions that I'm going to try to answer next time.
Speaking of fantastic questions, I'm going to ruin it by asking a fucking whack one. Is there methionine in meth? Amphetamine?
So strictly speaking, there's not methionine, the amino acid, but like there's a reason, let's say there's an overlapping reason, generally speaking, as to why we call methionine, and why we call, methamphetamines. Sort of like, well, it goes back to like organic chemistry of like, why do we call something acidic? Because, or let's say, why do we call something a carboxylic acid? Because it has this little like this little conformation, this little motif of atoms. And why we call something an amino group, where methionine has a methyl group, okay, and methamphetamines, they have like methyl groups. So the ultimate answer is no, you don't find methionine in methamphetamine, but there's an overlapping, theme to them, technically speaking. But good question, absolutely.
Sick. Well, thank you. I look forward to next Wednesday.
Yeah.
That being said, I'm like 85% sure, but I am also like, I'm getting married next Friday. So like, that's literally the next week. So that one might be the fucking like, I'll let you know. There's an 85% chance that it'll be great, but things are getting to the wire on that. And then I'm done after that. And then I'm free for forever and no potential issues. So just a heads up.
Yeah. And if you want to like move it to potentially Tuesday or Thursday, or we could also skip next. I'm open. But like, yeah, I'm pretty flexible these days. But either way, congratulate. Well, congratulated, but like, yeah, that's awesome. I hope you enjoy your ceremony and wedding and reception and party and all that stuff.
It'd be good. It's just lots of like work and things like that. So I just, yeah.
I'm sure it's a lot of stress, but a lot of stress that I have no doubt like will be worth it for, the great day.
Yeah, it'll be great. It'll be awesome. Yeah, no, for sure.
All right. Well, class dismissed. I want to respect your time.
I appreciate it. Thank you, and thank you for your time.
All right, see you next time. Take care. Be well.
Have a good one. You as well. Bye.
All right. Jack, welcome. Thank you so much for passing by. And yeah, I might give some homework. Let me just close some things, some tabs. Sorry if I missed some of your chat. Let's see. It'd be well. So it's been a minute since I've actually calculated dipoles. I'll be honest about that. Where I haven't really. I'm definitely rusty on calculating dipoles because don't really do that, at least in my field, or at least for my work in my past research. Yeah, saccharides, carbohydrates, exactly right. No. Even I probably couldn't even remember technically the unit for dipole. Well, I know I've been reminded of it now since I saw it, debi. But yeah, if you ask me, let's say even last week, what's the unit when calculating dipole? I would probably have to think for a few seconds. Oh yeah, debi, because I just yeah, it's been so long. Even though I technically I still teach this stuff now. It's just maybe I'm just on autopilot that I'm just not paying attention to what I'm saying, because it's I don't know, moved into my intuition now or something. But yeah, as always, that was great. And I'm always trying to think of ways to improve. At some point I'm going to get a proper overlay, and hopefully at some point I'm going to get a green screen, and have maybe my entire background as the PowerPoint presentation. But yeah, all that to say is I'm looking at ways to improve for sure. So based off of your recommendation, Jack, from last time, I believe last time you mentioned covering the dark oxygen, since we covered Luca last time, the last universal common ancestor. We covered some research about that. And there's a hypothesis / theory that the last universal common ancestor started at a hydrothermal vent, deep in the ocean, because that would have been rich in hydrogen gas or molecular hydrogen, and it'd be rich in other nutrients as well. I believe iron, but don't quote me on that. And yeah, I definitely have seen the headlines of dark oxygen discovered in the past few weeks, or in the past 2 weeks. So, but first I want to start with, and I got, I think, the original research that was published recently, evidence of dark oxygen production at the abyssal sea floor. And then there's this other one published last year. Actually, I didn't check. Is this the same group? Thomas Kuhn, Marlowe. Looks different. But I also found a mainstream article to start with. I have not read this piece of research here, since I haven't had time to. I'm not even sure I'd be able to fully understand or appreciate it, since it's not my field. Maybe just go through the introduction and the discussion. But difference, yeah, probably. Let's see the affiliations. Additional acknowledgements. Nope. Additional information. Okay, here are the affiliations. Scottish Association for Marines, blah, blah, blah. Boston. And where author information. Calgary. Yeah, well, Calgary, Canada. So yeah, looks like totally different institutions. So 12,000 feet under the ocean surface is a world of eternal midnight. No sunlight can penetrate to this depth to promote photosynthesis, as in no primary producers, okay, or no autotrophs, where, you know, us as humans, we are heterotrophs. We rely on consuming basically other organisms to meet our energy demands, and pretty much ultimately that comes from plants, as in plants, through harnessing energy from the sun, they produce sugars, carbohydrates, that other animals eat and consume so they can grow, and then whatever, we eat the plants or we eat the animals that eat the plants. But yeah, since basically this does not occur at the bottom of the ocean because there's no sunlight, so you can't harness the energy from sunlight when there's no sunlight at the bottom of the ocean. So no plants are producing oxygen there. Yet, the life-supporting gas is abundant in this darkness-cloaked region, thanks to an unlikely oxygen factory, potato-sized battery rocks on the seafloor. New research published this week in the journal Nature Geoscience, which I believe is this one right here. Yeah, Nature Geoscience. Reveals that nature has devised a way to produce oxygen without the involvement of plants. It's an amazing and unexpected finding. Daniel Jones, a researcher at the National Oceanography Center in the United Kingdom, who wasn't involved in this study, tells CNN's Katie Hunt. Previously, scientists had understood oxygen to be the product of life itself, namely created by photosynthesizing autotrophs, such as plants and algae. And again, autotrophs pretty much means, you know, organisms that can produce their own food, like plants. But the new study overturns that simplistic narrative. In fact, the discovery was so astonishing that when lead author Andrew Sweetman first measured this dark oxygen in the Pacific Ocean's Clarion-Clipperton zone in 2013, he dismissed it outright. I just ignored it because I'd been taught you only get oxygen through photosynthesis, which is largely what I've been taught as well. Sweetman, an ecologist with the Scottish Association for Marine Science, tells Victoria Gill of BBC News, "Eventually, I realized that for years I'd been ignoring this potentially huge discovery." Sweetman was part of a research team aiming to measure how much oxygen was being consumed by organisms at the bottom of the ocean. What he saw in the seawater scooped from the deep was a rise in oxygen levels instead of the predicted decrease. Initially, he thought his sensors were faulty and sent them back to their manufacturer for recalibration 4 to 5 times. In 2021, the opportunity came for Sweetman to return to the same spot, this time to survey the seabed for a deep-sea mining firm called the Metals Company. Using a different technique, Sweetman's team once again measured dramatic increases in dissolved oxygen, writes Scientific American's Alison Parshall. He finally had good grounds to take the numbers seriously and motivation to hunt for the oxygen's real source. First came a process of elimination. The scientists ruled out the possibility that microbes were behind the act in lab tests simulating the seafloor. The researchers killed off any organisms in the water with mercury chloride, yet the oxygen levels still rose. That region of the CCZ was dotted with rock-like lumps known as polymetallic nodules, which form when metals such as manganese and cobalt precipitate out of the water and coalesce around shell fragments or shark teeth. Scientists zeroed in on these metals as the source of the oxygen, but they still weren't sure how they created the gas. For instance, the oxygen wasn't due to radioactive substances in the nodules splitting water molecules or the decomposition of oxygen-containing minerals like manganese oxide. A breakthrough came when Sweetman was watching a documentary about deep-sea mining in a hotel bar in Sao Paulo, Brazil. According to CNN, he heard a character calling the nodules a battery in a rock, and an idea zinged into his brain. Could the oxygen be generated electrochemically? If you put a standard AA battery into salt water, you'll observe bubbles and hear a fizz. That's the generation of hydrogen and oxygen gases as the electricity splits water molecules, a process known as electrolysis. The researchers suspected the same thing was happening in the deep ocean, thanks to the polymetallic nodules. Indeed, voltage measurements on the nodule surface confirmed the rocks carried as much juice as 0.95 volts. It was a little short of the theoretical requisite of 1.5 volts for seawater electrolysis, but the researchers suspected that the nodules clustering together helped to create the reaction overcome this hurdle. This is one of the most fascinating things I in my lab have ever worked on. Franz Geiger, a physical chemist at Northwestern University and co-author of the paper, tells Scientific American. The naturally occurring rock batteries force scientists to broaden the theories of life's evolutionary trajectory. Scientists had assumed that complex life evolved after photosynthesizing cyanobacteria cooked up enough oxygen on early Earth. Perhaps life could have leveled up in pockets, feeding off oxygen in unlikely places. I think we therefore need to revisit questions like where could aerobic life have begun? And aerobic life just means life that uses oxygen or, aerobic respiration, to use the biochemistry terms. Sweetman tells Live Science's Sasha Pear the same process could also be playing out in other ocean worlds, such as Enceladus and Europa, which I guess these are moons of Jupiter, I think. Whether they had a hand in shaping life's evolution or not, the nodules are important to marine life today. A 2013 survey of the CCZ found that half of the documented megafauna species, those large enough for the naked eye to make out, were present only on the nodules. The deep sea remains a poorly studied region for biodiversity, with up to 2/3 of its dwellers still unknown to science. Part of this, if they are not considering it within the paper and are not seeing an indication of such, would be pressure at those depths as well. This will make the sodium more reactive. Pressure is definitely an element, not a parameter to take into account when it comes to chemical reactions. I would have assumed. Oh yeah, moons of. Yeah, you are correct. Definitely not Jupiter. Jupiter, the gas giant, right? Where definitely pressure is a parameter when it comes to chemical reactions. I'm not an ecologist or a geoscientist, but I would just sort of assume that sort of intuitively or obviously they would take that into account. But who knows? We'll see when I try to read some of the paper. Let's see. However, the CCZ is already attracting interest for its deep-sea mining potential. Their nodules that perform this oxygen-generating alchemy are also a mining target for their richness in rare earth metals. These elements, which include cobalt, nickel, copper, and manganese, are important constituents in batteries, smartphones, wind turbines, and solar panels. So, I don't know how I feel about mining the deep ocean. My intuition sort of lead me to not to do that. Deep sea mining, which is still in an experimental phase rather than a full-scale industry, has garnered immense backlash. So far, 27 countries and 52 corporations have pledged support for a moratorium on deep sea mining. More than 800 scientists and policy experts have petitioned against the practice. Mining activities in international waters, such as the CCZ, are regulated by the International Seabed Authority, which issues permits for mining exploration. Well, between the two of those planets, there are like 200 moons, easy to mistake. Although I shouldn't, I need to brush up on my moons of Saturn. Definitely my astronomy is rusty, for sure. I have tunnel vision on, biology and biochemistry. Exactly. Once we find something that we can exploit, that's pretty much our first go-to of, let's extract as much as possible. Without, considering, long-term downstream consequences. But like I understand, from what I understand, we're consistently looking for new sources of these rare earth metals, right? Since we're now using them continuously for more and more devices and, technologies. And so, it's demand driven, essentially. The Metals Company, the same firm that sponsored the new study, was the first to receive authorization for a mining trial in 2022, to the surprise and dismay of conservationists. To date, 16 deep-sea mining contracts have been awarded to private companies to survey approximately 400,000 square miles of the seafloor in the CCZ. Studies like Sweetman's are important to uncover the full scale of what's at stake. I don't see this study as something that will put an end to mining, he tells BBC News. But what researchers can do, he adds, is gather the data that can help stakeholders make informed decisions and possibly spark new ideas about how to minimize the fallout, if or when the industry ever gets off the ground. I mean, yeah, I agree with you. Not only like recycling, but also, you know, not having the need to upgrading your phone, you know, every year or every 2 years, or, you know, the sort of a planned obsolescence. Where, you know, I'm still using my Samsung Galaxy S20 that I got in the end of 2020. So going on 4 years, still holding strong. And, you know, if I can help it, I don't plan to upgrade for a while. You know, I could technically if I want to. But yeah, it just seems like, you know, there's ever increasing, you know, company pressure and social pressure to like upgrade your phone. Since, you know, it's expected that you have, you know, the newest gadget always on hand. All right, let's try and find out, or attempt to find out what this paper is doing. Although no guarantees that I can figure it out. Yeah, I try. Not only do I try not to upgrade like my devices that frequently, like, I mean, I still have my, I don't know if you can see, this is my Samsung Galaxy S6 Edge, okay, with the edge there. Well, I don't use it as a phone, but like, well, I use it mostly actually for the heart rate monitor, since this was the phone that had the ability to, like, you know, put your finger on and get your heart rate, and I still use it for that technically. But like, I had my S6 Galaxy Edge, or I was using it for like, I don't know, 5 years, 6 years, maybe longer. But yeah, I try to go quite a while without upgrading phones, since I do feel pretty guilty each time I upgrade. So, abstract. Deep seafloor organisms consume oxygen, which can be measured by in situ benthic chamber experiments, which, yeah, I don't know what these experiments are. I guess maybe I'll try and find out with the methodology. Here we report such experiments at the polymetallic nodule covered abyssal sea floor in the Pacific Ocean, in which oxygen increased over 2 days to more than 3 times the background concentration, which from ex situ incubations we attribute to the polymetallic nodules. Given high voltage potentials up to 0.95 volts on nodule surfaces, we hypothesize that seawater electrolysis may contribute to this dark oxygen production. Okay, so basically some reaction with the seawater is generating oxygen. At least that's what they're thinking, based off of their experiments. And at least based off of this description, it sounds like, you know, they are conducting experiments like on the deep ocean or the deep sea floor, or doing some sort of incubation on the deep sea floor. I wonder if that's true. Yeah, there's definitely bacteria down there. In terms of like the metabolic processes, I believe it's pretty complicated. You know, there probably is. Well, there's probably just about every organism that can break down just about anything on the deep sea ocean floor. Since, I mean, pretty much, at least as far as I can tell, okay, if there is some sort of material that exists, you know, either naturally or artificially, like, you know, humans have engineered or made it, like plastic, there's probably some organism that can, like, break it down somehow. As in, like, you know, as a result of, well, I don't know if it's the results, but, you know, there are definitely bacteria consuming or bacteria degrading bacteria. Plastic degrading bacteria. So oxygen is prevalent in deep sea surface sediments where its rate of consumption reflects the sum of aerobic respiration and oxidation of reduced inorganic compounds produced by anaerobic decay. These processes define sediment community oxygen consumption, or SCOC, and quantifying SCOC is needed to estimate fluxes of major elemental cycles through marine systems. We undertook multiple in situ benthic chamber lander experiments to measure abyssal sediment community oxygen consumption in the Nauru Ocean Resources Inc. blah 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 Clarion Clipperton Zone, where polymetallic nodules cover extensive areas of seafloor. Sediments and nodules were exposed to different experimental treatments, which included the addition of dead algal biomass, dissolved inorganic carbon, and ammonium, or cold-filtered surface seawater. No injection controls were also performed. In contrast to previous deep-sea oxygen flux studies that only showed SCOC, we consistently found that more O2 was accumulating in the chambers than was being consumed, resulting in net O2 production. Okay, so it seems, at least based off of in situ, if I remember my translation correctly, in situ basically translates to in place, or Latin for in place. So it sounds like they did these, in place on the deep sea floor. Constant linear decreases in O2 optode readings were observed in 2 experiments. Yeah. I'm definitely more used to in vitro, in glass, versus in vivo, or in silico, whatever, all the fancy terminology. But yeah, constant linear decreases in O2 optode readings were observed in 2 experiments. Figure 1, and SCOC determined by in situ O2 microprofiling was 0.7 millimoles O2 per day or something, indicating that SCOC occurs in Norides as in many abyssal habitats. Well, yeah, that makes sense. I'm definitely more used to the in vitro, in vivo dichotomy. However, O2 concentrations in 25 benthic chamber incubations started at 185 micromoles per liter and reached O2 max between 2, indicating net dark O2 production. Okay. Incubation time, hours. So this is figure 1. The in situ benthic chamber lander deployments were made during the 5 cruises in RD, present all incubations. So it seems like, at least from what I can tell, whatever, they basically, they created these, microenvironments or closed chambers in the deep sea floor and basically monitored how much oxygen is being produced over the course of a few days, or, 48 hours or 45 hours, a couple of days. And it seems like some of them you just have increasing concentrations of oxygen over time. Let's see. What does... want to get to the... okay, yeah. Net dark O2 production, DOP. Okay. Several lines of evidence indicate that net dark oxygen production was not caused by experimental artifacts. As in, basically wasn't the result of, a mistake. Or, something as a result of their experimental conditions. It really appears to be something, as in something is producing oxygen. So first, the total O2 change between the experimental and control treatments was statistically indistinguishable, and a steady increase in O2 concentration was recorded over many hours in multiple experiments. These observations demonstrate that net dark oxygen production was not attributable to the injection of exogenous fluids. Second, diffusion of O2 from trapped air bubbles within the chamber was unlikely because each chamber uses two one-way valves in the lid to purge air from the chambers as the lander sinks. Even if an air bubble could be trapped long enough to reach the sea floor, gaseous diffusion of O2 into the water phase would take less than a second at 4,000 meters depth, which is inconsistent with the steady increase in O2 over many hours seen in multiple experiments. So they're saying, like, at least from what I'm understanding, if it's the result of, like, a bubble or oxygen trapped in a bubble, like, they would see a spike in O2 production or O2 production, as opposed to what they observe. It seems like they observe like this steady increase over time, or like this steady increase into like a plateau, which is interesting. At least for me, it's sort of I'm curious as to why, it's not just this steady sort of infinite increase. I'm curious as to why it plateaus, although it could just be that, I don't know their system, but if it's like a closed system, then, there's probably some saturation point of like, yeah, there's just too much oxygen that you can't have any more in there at some point. I'm totally speculating on that. Let's see. Third, intrusion of O2 from the plastic chambers into the water phase is unlikely, as they are built from polyoxymethylene, which is both highly inert and chemically stable in well-oxygenated settings, and would not explain the variation in net dark oxygen production, because all experiments used identical materials. Last, net dark oxygen production was also observed during 48 hours ex situ sediment incubations. Okay, so yeah, whatever, ex situ or not in place. Several lines of inquiry were pursued to explain the net dark oxygen production. Subsurface advection of oxic bottom water from seamount flanks into seafloor sediments. I don't know what that means. And then into the chambers was discounted based on in situ O2 microprofiling that showed pore water was a net sink for O2 and undersaturated compared with the O2 seen in the chambers. Okay, so this is all just technical jargon to me. Furthermore, net dark oxygen production was measured in sealed ex situ experiments that prevented O2 intrusion from below. It is unlikely that biological mechanisms were responsible for the bulk of the net dark oxygen production, as ex situ core incubations revealed a net dark oxygen production in the presence of poison. Okay, so it doesn't seem to be originating from life, since, they apparently used something that should kill any life in there, or any microorganism in there. Whereas many microbes in the CCZ are able to detoxify mercury, or mercury 2 to mercury 0, and some microhabitat pore spaces in the core may have remained mercury chloride free, the taxa known to be capable of net dark oxygen production, for example, this organism, are killed by its addition. We also observed weak statistical support between the relative abundance of certain nitrogen cycling microbial taxa and net dark oxygen production. The fact that net dark oxygen production was detected in ex situ controls containing only polymetallic nodules suggested that the net dark oxygen production was linked to their presence. Hence, we estimated the potential contribution of radiolytic O2 production using a kinetic model and found 0.18 micromoles per liter O2 would be generated by this process within 48 hours. We also modeled the chemical reduction of manganese 4 oxide at an in situ temperature across a range of pH and O2 conditions encountered at the seafloor to assess if this reaction could liberate the O2, but found that less than 0.1 nanomoles of manganese 4 oxide would be chemically reduced to manganese 2 at seafloor conditions. As such, localized radiolytic O2 production from the sediments and nodules and chemical dissolution explain only a negligible proportion of the net dark oxygen production observed. So it seems like, through process of elimination, okay, they come to the conclusion that, like, yes, it's not microorganisms that's producing this oxygen, and that as a result of, like, their controlled experiments, it seems like it's through these nodules and some sort of chemical reaction, and it seems like they're able to sort of, like, model it as well. So, the oxygen evolution reaction requires an input voltage of 1.23 volts plus an overpotential of approximately 0.37 volts to split seawater into hydrogen gas and O2 at Nori D's seafloor, mean pH 7.41. This value can be lowered by several hundred millivolts if the reaction proceeds via the lattice oxygen-mediated mechanism. Use of metal catalysts such as manganese oxides enriched with transition metals, for example nickel, found in nodules and characterized by large tunnel areas and abundant defect sites, can optimize the adsorption of reactants and enhance conductivity and catalytic performance. So it seems like, so at least if I'm understanding this correctly, okay, there was this barrier, this voltage barrier that they thought couldn't be crossed in terms of, like, basically splitting seawater, where it requires basically this much voltage, okay, that based off of their calculations, like, is not naturally there, as in you cannot generate oxygen from splitting of seawater because, like, the voltage is not there to do that. But then based off of their analysis and sort of the unique conditions in this sea floor of, like, you have certain metals that might serve as catalysts, and some other things unique to this particular environment, that voltage threshold can be overcome, or more specifically, that voltage threshold can be lowered in terms of you don't need this higher voltage. You only need, a lower amount of voltage because these unique conditions in this deep sea floor. Yeah, it could still, at the end of the day, this is scientific research, and so, they're going based off of their best interpretation of the evidence, but this is not like, the nail in the coffin of, like, it has to be this and only this. At the end of the day, there's always that possibility that we haven't considered or something we've overlooked. Unfortunately, research is never perfect. So yeah, this you're right, it does not explicitly or 100% rule out some combination of bioactive, chemoactive, or electroactive, or even, like, just also doesn't 100% rule out that, like, yeah, it's also coming from some other microorganism that they just don't know about. You're looking at the box, I guess there may be towards the end or in the supplemental. Well, I guess we'll get to it. Where even them eliminating, them eliminating of, like, their conclusion is, like, well, this oxygen production is not coming from life or a microorganism because, they use a poison. They use mercury chloride or some variation thereof, which, that should be killing everything there. Even though there's microorganisms that might not be killed, okay, by the mercury chloride, but as I believe they say, it's like, well, even if, okay, the mercury chloride is not effective at killing everything, okay, the only organism that, at least we currently know of that's possible to do this, well, that would be killed by the mercury chloride. But still, that doesn't eliminate the possibility of, like, well, maybe there's some other microorganism that, we just don't know about, or, we haven't discovered. that like is actually there, but we don't know about it, or like, you know, well, it's there, and it's not being killed by the mercury chloride. Let's see. Where was I? I think I was around here. Oh yeah, pretty much wrapping this up. So yeah, we tested the electrical potential between 2 platinum electrodes at 153 sites on the surface of 12 nodules from the UK1, NORI-D, and Bundesandstalt. I'm not going to attempt to pronounce that. License areas, although the potentials between different positions on the nodules were highly variable. Potentials up to 0.95 volts were found, and high mean background corrected potentials were detected under cold water conditions. On the basis of these studies and net dark oxygen production being observed in nodule-only ex situ incubations, we hypothesized that the net dark oxygen production may have partly resulted from seawater electrolysis, with the necessary energy coming from the potential difference between metal ions within the nodule layers, leading to an internal redistribution of electrons. Whereas questions remain concerning this potential mechanism, such as the identity of the energy sources, longevity of net dark oxygen production, catalytic stabilities, electrochemical conditions on exposed versus buried nodules surfaces, and the influence of different chemistries within the nodule layers. The geo-battery hypothesis was supported by the link between DOP and nodule average surface area. This connection could be due to an increased abundance of anode and cathode sites, or a greater abundance of high nickel and copper dendritic porous layers in large nodules. More, you know, technical jargon. Assuming the geo-battery is part of the response for the initial high DOP rate may have been related to, well, yeah. This is all stuff that I cannot fully dissect. So, let's see if I can extract something from this. Nodules were collected in NORI-D. Okay, so this is them. Box and whisker plots of background corrected voltage potentials on nodule surfaces. So they basically measured the voltage in these areas, or in these specific nodules of these areas. There are methods. I'm definitely not in a position to dissect their methods. Let's see. Oh. There's no formal discussion. Interesting. Let's see their supplemental. Oh. Are these all Excel files? Oxygen opto concentration. Oh, okay. Like microsedimentation leading to, let's see, leading to certain salinity variables at depth. In doing so, it creates factors needed to form the nodules. Then, as the nodules form, they are then creating further interaction with their environment. Yeah, that's essentially my understanding in a nutshell as well. Interesting. So not only do you have supplemental data, but you have extended data as well. Interesting. Benthic chamber lander and multi-core deployment locations. Okay, this is just showing where their in situ experiments took place. Extended. Okay, here are the oxygen concentrations. Nothing super informative there. Well, they're definitely providing a lot of data. Bar chart showing total net O2 production in ex situ sediment cores. Okay, so pretty much the total oxygen. You have your control. Interesting. Okay, and the various treatments. So yeah, here's their mercury chloride. Okay. And it seems like, you know, assuming the mercury chloride is like killing the microorganisms, or most or all of the microorganisms, then you see, at least you see some of the oxygen, the total oxygen, go down. And the nodules, okay, so yeah, no treatment. Interesting. Phase stability and solubility of bernicite. I don't know. Yeah, definitely can't interpret that. Interesting. Supplementary, source data. Okay. Okay. Let's see if they're like pressure chambers. I assume it's in the methods. A Bentham chamber lander was deployed, yes. Lander weighted before the sediment integrated and enclosed microcosm. Yeah, so it seems like they're just like, you know, they're just inserting these chambers and trying to create something that's, you know, just like this enclosed environment, or as they say, well, the microcosm of the seafloor. 10 minutes into the incubation period, the enclosed chambers were injected with 50 ml of one of three solutions, 0.45 micrometer filtered. Okay, so this 0.45 micrometer filtered, you know, there's a reason why we use that size filter, because, you know, it's supposed to filter out any microorganisms, as in bacteria, generally speaking. On average, your typical bacteria is 1 micrometer, okay? And so since this is smaller, okay, this should be filtering out, it should be, not necessarily guaranteed, although we, generally speaking, in biology and biochemistry, like when you filter water through a 0.45 micrometer filter, we like consider it essentially sterilized. Yeah, containing, well, I wouldn't expect you to know, but like, yeah, these are standard filters, like that you can buy, syringe filters specifically. That they're just these adapters that will fit onto your standard syringe that, you know, whatever you can buy, whatever, at a pharmacy. Like if you wanted to, like, you know, filter sterilize your water, you can do that. Not really necessary when, you know, these are expensive. Well, you get a box of these for $268. But that's typically what we do, you know, for research purposes. If you want to make sure that at least our water is bacteria free, it would not be virus free. Yeah, well, to make a filter like that, it's not an easy thing. Oh no, I need to correct. The record. This 0.45 is slightly bigger. To truly filter sterilize, you need 0.22. That's what you need. These would be more expensive. So you go even smaller, about half the size, well, a little bit less than half size, and obviously these would be more expensive. But it's still the same thing. It's still a syringe adapter. So the technically, okay, the 0.45, not strictly speaking sterilizing. It's the 0.22 that would be sterilizing. A little rusty on my filter sizes, or pore sizes to be more specific. Not that that's, you know, a huge major detail. Yeah, exactly. Where, well, the goal is like it should be, as in these 0.22 micrometer, okay, diameter syringe filters, as in you pour your water, well, first you add this will stop the water from passing through, like you have to actually apply pressure, but like, yes, that is the primary reason as to why we do it. Like if you take your distilled water, so your distilled water is supposed to be also, you know, sterile, okay? But we try to go the extra mile of like, well, you know, with some extra security, okay, we'll pass it through a 0.22 filter, and that should filter out all bacteria, or like virtually all bacteria. Assuming you do it appropriately, like, you know, let's just say, you can easily, since you generally do it in a lab, like in a somewhat open setting, okay, you got to make sure that, you know, you're not just like, you know, filtering your water into like, you know, a glass, okay, you gotta have the water go into a sterile container as well. These would be pretty much almost exclusively in lab or research conditions, yes. This would not filter out viruses or viral particles, but it should filter out virtually all bacteria. Since like your average size of bacteria, I believe, is about one micrometer, around the order of micrometers. So yeah. Since most bacteria is around, you know, in the, you know, 1 to 2 micrometer range, but not all. There are some, that's why I said there's always exceptions. But basically, they are bigger than this 0.22. And so they should not pass through the filter. Where do diversity, structure? Oh, this is just your standard encyclopedia. Small but mighty cell size in bacteria. Well, individual cell volumes, yeah, but I'm mostly interested in diameter. Let's go with diameter. I guess they don't give an average diameter. There you go. Most large bacteria either maintain a high surface to volume ratio, being long and thin, like Spirochaeta, blah, 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 250 micrometer long, 0.75 micrometer diameter. But like, yeah, diameter wise, your average size is roughly, you know, 1 micrometer. So yeah, they will not pass through this. The one that they're using, this 0.45, that would still filter out, okay, most bacteria, but it would not be as sterilizing or, you know, as good as the filter as the 0.22. Well, so it depends on, so definitely you would need to get pretty much, well, if I remember correctly, although my virology is a little bit rusty, but there are some viruses that are on the micrometer range, okay, pretty much the size of bacteria, actually. But I think there's only like 1 or 2. Or like just a really, those are the exceptions, not the rules. Where, let's see, there is, yeah, the giant discovery of the giant mimivirus. But like, yeah, you would need to get into like the nanometer range. So even this one, okay. This mimivirus, I think there's a maxivirus, I think. But yeah, the virus has a capsid diameter of 4 to 500 nanometers, okay, but this 500 nanometers, that's the size of 0.5 micrometers, okay, where it would be filtered out. This one would technically be filtered out by this 0.22 filter, as in 0.22 micrometers, that's 220 nanometers, okay. So since this particular virus is, 4 to 500 nanometers, this would not pass through the filter. So basically, this virus is like pretty close in size to some bacteria. But yes, generally speaking, viruses are much smaller, on pretty much, single or double-digit nanometer size. And the question of are there organisms that we interact with that's smaller than viruses? I guess if you're using the word organism, I guess technically no, unless you want to consider like a prion, okay, an organism, which, that's, I guess, a philosophical debate. But yeah, strictly speaking, there's no cellular organism that we interact with that's smaller than a virus. At least not as far as I know. Maybe there's been some new discovery. But that's what I learned in my microbiology. Okay, so their chambers. 79 or freeze-dried some sort of algae, still an organism. And then they injected sodium carbonate, ammonium chloride dissolved in cold artificial seawater, salinity 35. 0.45 filtered cold surface seawater. Solids control, conditions to be measured. Yes. Two days before the first liner cruise. Okay. Yeah, hey, wherever you get your knowledge from, totally valid. Like, well, even now, like, my knowledge of viruses is pretty rusty. That's for sure. Or at least the nitty-gritty details of viruses. I can go through, like, the life cycle and some of the fundamentals of, virus structure. But if you ask me to start, like, classifying and, naming species of viruses, that's all, like, ejected from my brain, or repressed memories from my virology courses. Well, I'm surprised there's no formal discussion on this paper. I would have thought they would have wrapped up, but this is, okay, that's why. It's a brief communications paper. So of course, yeah, there's no discussion. Just as I guess this one as well. This is Nature Communications, so there's not going to be any discussion, unfortunately. No, it's because that's the Nature, sort of ironically. When they talk about communications, and anytime that you have communications, pretty much that's our fancy, sciencey way of saying this is a short article, and there's not going to be any discussion. It's sort of just like, here's a reporting of our results, and it'll have an introduction. And like, here's our introduction, methods, and results, and that there's not going to be any like formal discussion. I'm not going to put it into context. They're not going to, talk about future research and implications of this research. Generally speaking, communications papers, they typically have like a page limit. Although one of the, it's not a surprise that this communications paper has both extended data and supplemental data, since that's one of the ways, okay, that researchers bypass the page limits of communications papers. It's like, well, yeah, we'll follow your page limits. Typically, it's going to be like 3 to 4 pages. I'm pretty sure if I check the PDF, okay, in terms of text and all that stuff, it's going to be like 3 or 4 pages. 1, 2, 3, yeah. See, you know, and then there's the methods and all that stuff. Because when it comes to communications papers, they put page limits, but researchers bypass that of like, well, I'm just going to give you 20 pages of supplemental and extended data. Probably the same thing for this one as well. Data availability. But yeah, any journal that has, you know, communications in its title, they're going to be pretty short papers with no discussion, since that's how we, whatever. I don't know who came up with that convention, but that's like, those are the rules, so to speak. I don't particularly like it, but that's how science is done, unfortunately. So that's all I can extract. No, well, I'm sure there's a reason why, like, these authors, I mean, at the end of the day, like, I'm pretty sure they have enough data and results to come up with a full paper. Yeah, exactly. But let's say, for example, okay, we'll go to brief communications. Okay, there's a reason why they have this section here. Although, yeah. So we just went through this one, evidence of dark oxygen production at the abyssal sea floor, and then like when you open the PDF, you'll see that in terms of like actual text of, you know, introduction and results, it's like 3 pages, maybe at 4 max. And then if you check this one, this other brief communication, okay, it's gonna be like the exact same thing. Of like open it up, and page 1, page 2, page 3, and then it ends. Because that would be the rule when it comes to communications paper, of like you are limited by 3 pages, and that's it. And you know, I don't know if these authors are like, you know, there's always the trade-off of, I mean, at the end of the day, okay, many scientists, or most scientists, they're trying to publish in prestigious journals. So it's like, well, what would you prefer? Let's say what looks good on your CV. Of like, let's just say, it looks better if you published in Nature Geoscience, even though it's like just a brief communications, okay? Where it's literally only 3 pages of, you know, introduction and results, as opposed to, you know, if you publish in a less prestigious journal, okay, that, you know, you can have like a full write-up of 20 pages, right? You could be more thorough, but you know, that doesn't look as good if it's not as prestigious of a journal as like Nature Geoscience or whatever, Nature whatever, pick your Nature. This one's Nature Communications, same thing. You know, if I look at this one, Nature Communications, okay, it's gonna be, this is page 1, page 2, page 3, page 4, page 5, 6, even then this one, they're all gonna, so this one has a little bit longer of a page limit, it looks like it's 6, and even then you can see, like, is this a page when it's literally just figures, right? But in terms of text, there's not that much. This is like 1.5 pages so far, 2, 3, 4. There's like, yeah, 5 or 6 pages worth of text. And yeah, if I look at all the communications articles, they're going to be the same, just short. Well, they would charge you a lot to publish that, that's for sure. I mean, they already charge a lot just to publish, whatever, 10 pages. So yeah, 518, you know, unless you're wealthy, or you get some massive grant to publish it. So, I mean, I covered as much as I could in the dark oxygen paper. There's this one as well. I think I'll save this for another time. And well, it seems like this Smithsonian article is a pretty decent summary. I got more out of this than reading the actual paper. So that's pretty much all I had prepared for today. Before I go, let's see if I can do today's New York Times connections. Although I'm gonna hide the chat since I don't want help from the chat. Well, some of this is a little bit. Microwave, X-ray, visible rays, radio waves. Well, this is basically... This has to be electromagnetic spectrum. This seems to be pretty easy. And I guess I'm lucky that I can make the connection. As in, I know the electromagnetic spectrum pretty well. There, okay. There has to be some sort of connection between dishwasher, RAM, byte, server, comedian, cook, stuff, host, pack, drill, bridle, jam. So I mean, there has to be some sort of connection between dishwasher and server, and host, and cook. I mean, this just seemed like restaurant positions. If it's not that, I'd be very surprised. Restaurant jobs. Comedian, RAM, stuff, byte. Well, okay. Jam, stuff, RAM, drill. As in basically whatever. Stuffing something, jamming and ramming something. But then drill or pack, I'm not sure. Although I have some guesses. Well, no. Like these. Okay, let's go with pack. Well, I have no idea what the connection is between these last four. Today's puzzle, pretty easy. Not that challenging. I definitely failed on last week's, that's for sure. But I have no idea how these are connected. Byte, I'm not even sure I know what bridle is. But whatever. Obviously, I don't need to know, since that's all that's remaining. Things with, okay. I guess that. A bridle bit. I'm not even sure I 100% know what they mean by bridle. Oh yeah, definitely related to Luca, and as you said, the non-organic O2 production. For sure, yeah, I'm super glad that you suggested it. Yeah, I'm seeing, well yeah, since that's what popped up for a bridle. I don't know. A bridle is a piece of equipment used to direct a horse. Okay, well, I think I've maybe ridden a horse like once in my life. Like 25, 30 years ago. Here is where I fail pretty badly. Oh, Noah to Bud, welcome. Great to see you. Hope you're doing well. Saving with them. Fair enough. I'm gonna hide the chat for now. Let's see if I can guess this. My intuition. Okay, I'm really bad at these. But I just want to say, you know, whatever. Russia, Eastern Europe. So I'm just gonna go, you know, with whatever the simplest. Somewhere in Moscow. Now the year from the cars, I don't see any cell phones. I'm not even sure I have my Russian guess correctly, given what I see of the population, but I can't recognize languages all that well. I see CCP here. Look like this person's on a cell phone, so whatever, at least, whatever, 2005, 2010 later, looks like a smartphone. And the makes of the car seem pretty recent, okay? So I'm thinking at least, whatever, 2010 onwards. In terms of the country, I mean, based off of this writing here, I would have thought either Russia or Eastern Europe, but I have no idea what this language is. I'm gonna choose a year. I'm gonna go with 2015. I'm pretty sure I have the country wrong, but I don't know what country this would be. And the license... No, I don't see anything on the license plates. Yeah, no, I can't have no intuition on this language. Way off. Okay, not super off with the year. This is Tajikistan, okay. So I was way off on that. Okay. Well, I see American flag, British flag. Closing date for applications, 8th November 1976. I have no idea really what I'm looking at here. Rugby. Okay, so it's not, should not be North America. Have I joined the Union? I mean, this looks like somewhere in the UK. And you know, somewhere before the 8th of November 1976. But I literally have no idea what I'm looking at. Oxford University Orchestra. I mean, it's a black and white photo, and, well, they had color photos, you know, in 1976. Or whatever, around those years. But yeah, I don't have any idea. But my intuitions lead me to somewhere in the UK. I'm gonna go with the stereotypical London. And we'll go with whatever, 1974. Okay, well, I guess my intuitions. So so a notice board in Oxford University's Bodleian Library. Okay. I think I got a little bit lucky there, or I don't know. Maybe I just overthinking it. Next round. I have no idea about this one. Obviously a fairly old picture. I would put it, cars in the back. Maybe around the 70s, somewhere. But in terms of country, like, I have no idea what this color theme is. I don't know what this ceremony is. I'm obviously not culturally informed. I'm gonna go with 1975. But yeah, I can't see any, at least not based off of my knowledge, anything obvious in terms of country. People smoking. I'm just gonna go with whatever. Rome, Italy, for virtually no reason whatsoever. 6 years off. Okay. Festivities in Siena, Italy for the Palio di Siena, a biannual horse race dating back to the 17th century. Okay. I'll take it. Not the worst. Okay. Cars. I don't know if this is like a deceptively old photo or like a stage photo that's to look old but is actually recent. Nobody in the background is like on a cell phone. You have H&M. So I don't think this is like a legitimate, I don't, like, H&M's not super old. I'm pretty sure. This seems like a staged photo. At least I don't think H&M is super old. The cars in the background make me think like 90s. Or maybe at most early 2000s. And not, pretty sure not North America. Well, actually, I don't know. I mean, based off of this signage, I don't think I've ever seen that anywhere in North America. I am going to go with, like, I don't know. Yeah, I think those cars, that's like late 90s, early 2000s cars. Can't see the license plates. I'll go with like 2005. And yeah, I don't know. Since I have no idea, I just get the intuition of somewhere in like the UK. So I'm just gonna go with London again, or whatever. I'll switch it up, go with Birmingham. Alright. This is Sweden. Okay, 2012. I'll take it, not the worst. This is Swedish history writer Christopher O'Regan riding a bicycle with fans through Stockholm. Okay. I don't know. I mean, I see a Jewish population. I believe. So, you know, I just want to say Israel. But I could also just be ignorant. Like, I can't identify any of the text or the writing. Well, I mean, yeah, I see some sort of translation there. So I'm just gonna go with somewhere in Israel. Based off of the cars, I want to say probably 60s. Got a bus. We'll go with 68. But like, yeah, I mean, this could all just be a misdirection with the Jewish population. I guess we're go with Tel Aviv. I was okay. Well, I got the year way off, or well, pretty off. Location not too bad. A busy street crossing in late 70s Jerusalem. I'll take it. I've had better, I've had worse. Spain, I assume that was with the one with the yellow and blue uniforms. Oh, yeah. I was totally off with the Tajikistan one. I was nowhere close to that. Yeah, I think I got pretty lucky. Pretty lucky with the connections. That wasn't a super hard one. Alright, so that's all I had planned for today. I should be back. I'm planning to be back probably on Sunday. So, well, I'm gonna put in the Discord, but I have written up, my experience. I've written a Substack, technically, of my experience working for a biotech company, or the one that I was hired and fired within 5 days. And so I wrote up my entire 5-day experience there, and you know, what transpired there based off of my perspective, including audio recordings. So I plan to go over that on Sunday, or hopefully Sunday. I plan to get back to regular streaming on Sundays. And then there's research that I want to cover if there's time left, but definitely on a stream soon. I'm going to cover this paper, yes. Yeah, the blue and gold, I had no, like, you know, I just see, you know, blue and gold or blue and yellow and think Ukraine. Obviously, that's, you know, ignorance on my part. There's many other possibilities outside of that. But yeah, I'm going to be going over well, maybe as a preview. Let's see. Go to my dashboard. Posts in my drafts. Yeah. So, well, actually, what I'm gonna do, okay, this is technically not published yet, so it's not accessible to the public. Not that I expect anybody to access, you know, my Substack. But I'll put the link for this, okay, in the Discord. You know, the draft version, pretty much. Well, I've sent this to some people for editing and proofreading purposes, as in I sent it to Eucharist for his feedback, which his feedback has been super valuable. And I also sent it to Rich, iCal Rich, for his feedback, since he's almost certainly a much better writer than I am, given the fact that, he teaches literature. And, you're reading the Divine Comedy with him. So I sent it to him for his feedback, which I incorporated, and his feedback was invaluable. So I'll provide the link for this, the unpublished version in the Discord, and then what I plan to do, okay, before like fully publishing it to the general public, and like trying to disseminate it as widely as possible. I'll post the link to the private version in the Discord, and you can read it beforehand. It's lengthy, okay, so you don't have to read it, which is why I plan to go over it on stream. The audio recordings are here towards the end, because there was a meeting. There's a meeting that I recorded, a meeting that I legally recorded, as I say here in my opening paragraph, that I never intended to publish any of this, or write this up, or publish the audio recordings. Obviously, I've changed my mind, but even then, when I decided to audio record, I checked the laws, my local laws in my province / country of Quebec, Canada. And yes, Quebec, Canada is a one-party consent state. And as long as you're part of the conversation, you can record the audio. As I mentioned here, this was a meeting that was specifically held to give me feedback on my performance during those 5 days, although technically 2 days, really. I'm fairly certain that I was part of it. I think Eucharist and Rich should be go-tos for proofreading, editing, feedback. I can't emphasize enough that their feedback was invaluable. And I did my best to incorporate it. I might have failed, but I plan to, at the very least, go over this on Sunday, hopefully sooner rather than later. Like, this is basically, I want to be done with this in terms of, like, I've read this probably a dozen times by now, since, I'm a little bit paranoid in terms of whatever, correcting mistakes and editing, proofreading, blah, blah, blah. Since I'm not the strongest writer, or I'm very nitpicky about my writing. But then, I also plan to cover this research as well, which I think is pretty cool, in terms of research about chronic fatigue syndrome, or myalgic encephalomyelitis. Whoopsies. Didn't mean to do that. But yeah, that's what I have planned for, should be Sunday. Again, I'm trying to get back into the routine of streaming on Sundays. Right now, I just have the one day on Wednesdays, which is not enough for as much content as I want to produce. And so I'm trying to at least get back to both Wednesdays and Sundays, hopefully starting this Sunday. But at the very least, I'm going to provide the link to this in the Discord, so that if anyone wants to read it beforehand on Sunday, they can. Although I just plan to read this out, what I wrote on Sunday, and then make it available to the public next week. But that's all I had planned for today. Let's see if I can find someone to raid. I don't think there's anybody streaming particularly. No, there doesn't seem to be anybody particularly streaming. Not much in the science and tech as far as I can tell. Yeah, I mean, I don't want to impose myself. But if you had something planned on Saturday, I'd be open to joining it. I also might be streaming at some point some more political content, since I believe, Half-Baked Takes reached out to me to maybe doing a show discussing topics, from the left, me, and the right, him, representing both sides. I believe that's still sort of in the works, or in conversations about. But yeah, I'm always up for doing nerd stuff. Absolutely. But yeah, that's all I had planned for today. Again, plan to be back on Sunday. Thank you everyone for passing by and anybody that's tuning in. Jack, always a pleasure. Super invaluable. One, not only all the information that you provide in terms of, well, also just like correcting me on me getting the moons of Jupiter wrong, because, you know, I have my weaknesses in astronomy, or my knowledge in astronomy is rusty. And then, yeah, all the questions and the recommendation for covering the dark oxygen, super appreciated. I will absolutely do my best to attend. Thank you so much for the invite. I will check it out. So yeah, I plan to be back on Sunday. If not, we plan to do the lecture next Wednesday. But I'm trying to do my absolute best. Like, this Sunday is when I get back to streaming regularly on Sundays. But yeah, thank you everyone for passing by. No to Bud, thank you for passing by. Always great to see you. Hope you're doing well. And yeah, that's it for me. Until next time, take care and be well.